There's a number of different techniques for factorising quadratics, but they all really boil down to the same thing, and that is that to put brackets in is the opposite of expanding the brackets in the first place. Usually though it's more difficult to factorise than it is to multiply. Think of 15 times 17 is much easier to do, 255, than realise that 255 is 15 times 17. It's much easier to multiply than to factorise, particularly if we've got a calculator. Now, how did we first look at multiplying? Well, you might even have multiplied 15 by 17 by splitting it up into 10 add 5 and 10 add 7 and finding the area of this rectangle. This would be 10 times 10, 10 times 5, 7 times 10, 7 times 5, and then adding that lot up, we get that the sum equals 255. Now, we could do the same thing with algebra. Let's say we're multiplying x plus 2 by x plus 6. Then we could draw that as a rectangle, x plus 2 by x plus 6. And it doesn't matter about the scale, this is simply a sketch for diagrammatic purposes. It's not really meant to be accurate. Now, in here, I'd have x squared. Here I'd have x times 2. Here 6 times x. And here 6 times 2 to give the sum, the total of that lot is equal to x squared plus 8x plus 12. Now let's suppose that we're trying to factorise x squared plus 15x add 50. Now we know that it's going to have two brackets, but we don't know what goes in each of them. So let's look at drawing our oblong. The first bracket, whatever is in here is going to go along the top, and whatever is in here is going to go down here, or the other way around. It doesn't really make any difference. Now we know we've got to get x squared and 50, so I can fill those in straight away. It's the other two bits which cause the problems. Now what I do know though is that the other two bits add up to 15x, so what we do is we partition, we split 15x up into two numbers which multiply to make 50. The two numbers here must multiply to make 50, and they must also add to make 15. And the only two numbers that work there are 5 and 10. So I can write x and x there, 5 here and 10 here, and that should work to give us 5x and 10x. So I can write the answer as x plus 5 times x plus 10, or the other way around. It doesn't really make any difference. Now I'm going to attempt to factorise 3x squared plus 17x minus 6 in real time here. The first thing I'll do then is to draw out my rectangle. Although I don't particularly like it starting with 3x squared, it's not the worst, because 3 being a prime number must have come from 3 times 1. So we've got that bit there. The minus 6 goes there. Now I want the two remaining bits, they must add up to make 17. One of these numbers will be negative and one positive to make minus 6. And I suspect that it must be either 3 and 2 or 6 and 1. And now I look at 17, I'm already thinking now 3 6s minus a 1. So a bit of trial and error, a bit of practice, I can see that if I multiply 6 by the 3x to get 18x, and minus 1 times x to make minus x, then I do get the 17 here. Now I think that's a bit of trial and error, a bit of in your head trial and error, a bit of practice of these type of things. I'll do the next one in real time. So factorise 12x squared plus 7x plus 1. Again, I don't like the 12. 12's a nasty number in any of these because it's got so many factors. But the 1 I do like. 1 must have come from 1 times 1. Or it could be minus 1 times minus 1. But the fact that everything is positive makes me think, oh no, it must be plus 1 and plus 1. So now what I'm looking for is the bits here and here. Now I know it must be 6 and 6x times 2x, or 12x times 1x, or 3x times 4x. They're both going to be multiplied by 1 in these boxes, and these boxes must add up to 7. And the only numbers there, the pairs of numbers that I just said, are 4 and 3. So 3x, 4x gives us 3x there and 4x there. And so we end up with 4x plus 1 times 3x plus 1. This one looks slightly unusual compared to the others because there's no middle bit. I could consider that, I could sort of imagine that there's a plus 0x in the middle there and just do it in the same way as I have the others. X squared must have come from x times x, and the minus 9, well, must have come from 9 and 3, sorry, 9 and 1 with one of them negative, or 3 and 3 with one of them negative. And they're going to add to make 0x. The only one that works there is 3 and minus 3, like that. So we get x minus 3 times x plus 3. Now you quickly become used to these. When there's no term in the middle, when there's no x term, and we have a square number here and something squared here, then it's called the difference of two squares. And the difference of two squares is easy to factorise. It's the difference of x squared and 3 squared is x minus 3 times x plus 3. So the difference of two squares should be pretty easy to deal with. I'll just fill this in here. We've got minus 3x there and plus 3x there. That's where we've got no x term because it cancels. Okay, this one looks pretty daunting like some of the others have. 25x squared I originally didn't like, but then you realise it can only be 5 times 5 or 25 times 1. And the 4 must have come from 4 times 1 or 2 times 2. So there's not that many different numbers that we can try in the four spaces. If I write in here 25x squared, I'm guessing it must have come from 5x times 5x. And the 4 here, I'm guessing must have come from minus 4 and 1, or actually I'm thinking ahead here. If I did put minus 4 and minus 1 to give 4. By the way, the reason why I've chosen negatives is because the bit here is negative. Minus 4 and 1. This bit here would then be minus 20, and this bit would be minus 5, and I wouldn't get the minus 20 what I'm looking for here. I'd miss it. So that can't be right, which leads me to believe that the 4 must have come from minus 2 times minus 2. And just check, that gives minus 10x, which is the correct thing because it's the minus 20x. So it's 5x minus 2 times 5x minus 2. This is an example of a perfect square. Lastly, I'll look at factorising x squared plus 6x. Now, I wouldn't normally do this, but I'll just show you that this method will work for this. That's 0 there. So x squared plus 6x, we'll have x times x there. Now the 0 must have come from 0 times something. That makes that 0x. And so anyway, we can get 6x is there, so that must be 6. Of course, I wouldn't normally bother with this. I just write that as x times x plus 6 by noticing that there's a common factor of x both here and here.